So we want to talk about a simple pendulum, which is another example of simple harmonic motion. We were trying to find the period. So just to remind you, I have a mass of some m on a pendulum of length L. There's a pivot here. Remember that I call that mass at the bottom a bob. There is a gravitational force acting down, a tension force acting along the string, and we decided that the restoring force was the tangential component of the gravitational force. If I pull my pendulum out by some angle theta, then that angle is theta, and I can say that the restoring force is mg sine theta. This is all review. This is all stuff that we did. We looked at the torque of that restoring force around the pivot point and found that the torque was negative lmg sine theta. We also said that torque was equal to I alpha. And we had told or convinced ourselves that if we figured out what alpha was, we would be able to get to omega, and from omega we could get to what the period was, or the frequency, depending on what we were interested in. So because we're going to need this later, we're going to solve for alpha right here. And we'll come back to that equation when we talk about physical pendulum in a few minutes. And then I convinced you, I hope, that for small angles, we could let sine theta go as theta. Okay, we talked about it in terms of linearization. Nobody here took BC Calc, but it's also a Maclaurin series, and we actually did it by experiment. Okay, we went out, and remember, you can go out to about 15 degrees. And once you get beyond 15 degrees, it no longer works. The amplitude starts to affect the period. Remember, though, that you have to measure theta in radians for this to work. Okay, even though we speak about it in terms of degrees, that's because when you actually pull the pendulum out, you have to measure that in degrees, because how would you measure it in radians? That's just too weird. Okay, so it's just kind of a place where the physical reality intersects with, honestly, the math. Okay? So my expression for alpha becomes, and actually I'm going to write this on another page, it becomes that alpha is negative lmg over I times theta. And this is important because we have some criteria for a simple harmonic oscillator or for simple harmonic motion. One of those criteria is that the restoring force points towards the equilibrium position, which we actually figured out. Okay, thanks, Alf. Just put it up here. Like, oh, thanks. Okay, which we actually figured out, and that's why we were using the tangential component of the gravitational force. But we also said that to be a simple harmonic oscillator, F, or in fact alpha, was going to be equal to negative omega squared times theta. Or, as we also call it sometimes, that A of t was negative omega squared x of t. But I can use my thetas and my x's interchangeably. So if we compare these two equations, what can you tell me? Yeah. So this is telling me that omega is the square root of LMG over I. And then what am I really looking for here? What did I start this whole thing trying to find? I said it at the beginning of class today. The period. How are period and omega related? 2 pi over omega. Good, Gianni. Okay, so the period for a simple harmonic oscillator is going to be 2 pi times the square root of I over LMG. Think before you. Okay. And this will actually work for any pendulum, as long as the angle is small. And by small, I mean less than 15 degrees. But because I have a simple harmonic oscillator, I can actually come up with, because I have a simple pendulum, I can actually come up with a value for I. How do I find rotational inertia? What's the formula? No. Usually we say mr squared, okay, if I have a point mass. So because my string is, of course, non-stretching and of negligible mass, all I've really got is the pendulum bob, which is a compact thing. It's not a bowling pin. It's not a ping pong paddle. It's this compact mass. I can say that the rotational inertia is going to be ml squared, because L is the distance from the mass to the pivot point, or the rotational axis. Which means that we can rewrite T as 2 pi times the square root of ml squared over LMG, or 2 pi times the square root of L over G. So note that the period of the pendulum, it only depends on what? The length. Okay? So like Sari and Zoe said, it only depends on the length. So it doesn't really matter whether I put an elephant or a mouse at the end of my pendulum, it's going to have the same period. Is amplitude measured anywhere there? No. Okay. And finally, when your spaceship crash lands on a planet somewhere and you need to figure out how to get off, how are you going to be able to use this equation? What would this equation tell you? You pull some loose wiring out of your, what? It's going to help you find little g. Okay, good. It does, but everything that we've talked about here assumes that we're using a small amplitude. If you use a larger amplitude, then things get crazy and you have to put the sine theta back in, so you can't make the parallels and the comparisons that we did. Okay, and that's something that if you go on and take a higher level mechanics class, like I think they usually call it analytical mechanics, you'll cover things like that. Okay. All right. So in that lab that you do on Monday, you will look at how length, amplitude, and mass will affect the period. Okay, using your good laboratory skills. Okay, so one thing I want to do is back up and talk about a physical pendulum. Now, a physical pendulum is any pendulum that isn't a compact mass on the end of a string or on the end of a thin rod of negligible mass and radius. So a physical pendulum could be, I take a ping pong paddle and I drive a nail through it and I set it spinning. That's a physical pendulum. I could take although this is not something that we would be able to do, I could take my sloshy water bottle and put it on the end of a string and swing it back and forth. That's a physical pendulum. Not only is this not a compact object, it's sloshy and the water moves around. That's not something we could do. But we could take an extended object. We could take an elephant. We could take a really big disc and put it on the end of a pendulum. And that would be a physical pendulum too. So to express the period for this, we just go back to here. Okay, we go back to the expression that we had where we were actually dealing with I. So we say that the period is 2 pi times the square root of I over mgl. Actually, except we don't call it L, we call it H. Where H becomes the distance between the pivot point and the object center of gravity. Correct. Because then you could take your pendulum and you could play with it near a black hole. For all intents and purposes in this class, center of mass and center of gravity will be the same thing because you will be in a uniform gravitational field. But it's one of those definition things where we got to tell you what it really means in code so that you don't go off and make a fool of yourself by trying to apply simple physics to something more complicated. You got to at least know that it's a more complicated thing. Yes, but they'll be in the astronomy department or the astrophysics department, more likely. But there are specific classes on black holes. But you need a lot of math to do black holes. And a lot of physics. Okay, so as I said, you can in fact find the acceleration due to gravity on a planet using a simple pendulum. You could find it using a physical pendulum too, but it makes it harder. So your planet, you have crash landed on a planet, you need to get off. In order to know how to get off, you need to know the escape speed. In order to know the escape speed, you need to know the mass of the planet and the radius of the planet, which are not that easy to figure out. If your computer's down and you can't use your New World catalog, or New World Atlas, excuse me, and go through and get that information because you can't connect back to NASA, you need to be able to figure that out. That's why they call it the New World Atlas. It's a thing that has all the exoplanets listed in it. You can't download it, but it's got some pretty pictures. We used it in astronomy. Gianni knows we used it in astronomy. So when you had to describe an exoplanet, that's where you went, was the New World Atlas. So you're going to take a length of cord or whatever that you've pulled out of the broken circuitry of your spacecraft. You're going to find a nice compact rock. You're going to suspend it from a whatever alien tree branch it looks like. You're going to pull it out a little bit. It doesn't matter how much you pull it out, because as long as you keep the amplitude less than 15 degrees, you know that it's going to be, the period doesn't depend on the amplitude. So you're going to pull it out. Of course, with your wrist patch or your wrist communicator or whatever it is, you probably have Apple software embedded in your DNA code by that point. And of course, there will be a timer. So you set that timer. Am I going to measure just one swing? No. I'm going to measure many swings, right? How many? Yeah, but what's a good number of swings to measure? 10, because it's easy to divide by 10. 10's a really good number. It's a magic number, but it's a really good number. Okay. So, what? We do live in a base 10 system. Okay. So you make it swing back and forth, and you measure it, and then, because you happen to be stranded on our own moon, and the length of your cord was 0.25 meters, and you ended up with a period of 2.46 seconds, tell me what the acceleration due to gravity is on the moon. Then you got wrong. Try again. Did you square things? Did you not square things? But Jason said the square root to begin with. Yeah. Yeah. What did you get? No. 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 We're all starting from this formula, right? Can't believe I could do this. You're killing me, Smalls. So that's going to be T squared is 4 pi. Who? We have a winner. Right? Right? This would be the algebra, yes? So G is going to be 4 pi squared L divided by T squared. I am not substituting in the numbers because that is a step too far. So, you know, pi squared is 9 times 4 is 36 divided by 4 is 9. 2 point anything squared is going to be 4 point something ish. So you're getting like 9/4. So it's going to be 1 point something. It should in fact be 1.63. I sincerely hope you check your math before you leave the alien planet's surface, or else it's going to be a really short trip. I can only trust you, Jeff, so far. It's intuitive, but we're not going to riff on, we're not going to go there. All right. Give me a prompt. I can work with a prompt. All right. So sample problem number 25. Okay. So let's visualize this for a minute here. Is always swinging so that it's going towards the center of the circle. Okay? But what we have now is because the car or the cart or whatever it is accelerating, which it is, right? What kind of acceleration are we talking about here? Centripetal. Okay? So because I'm talking about acceleration, it can't just use T equals 2 pi radical L over G. Because it's not just the acceleration of the Earth that's affecting my pendulum. So if here's the roof of the car, and here's my pendulum, I have, and so this is not a free body diagram, but I do have the acceleration due to gravity, but I also have that centripetal acceleration. So when I'm in a situation like this, the G in the denominator up there for my pendulum period becomes what we call G effective. Okay? Because it's not just the acceleration due to gravity, there's another acceleration that's affecting the object. Okay? And you could see, if you remember, that we had, so if this is going to be the radial component, then depending on which way it's moving, this is going to be the tangential component. Okay? So both this and this are going to have a component in that direction. Okay? That whatever force it is that's causing that centripetal acceleration, it's going to be horizontal towards the center of the big circle, but it's going to have a component in the direction that the pendulum is moving towards equilibrium. Yeah, because I said it was not a free body diagram. And have I ever in my entire life with you written the force due to gravity as G? In this equation? Well, normally it's the acceleration due to gravity, but where it comes from is the force due to gravity. It comes from mg sine theta. So what you would do, although it's not the way we're going to answer this problem, is you would go back to finding the net torque around the pivot point and realize that you would have a gravitational force and you would have a centripetal force that are going to act together. Okay. So we say that G effective, especially because those two components are perpendicular to each other, is going to be regular old G squared plus AC squared. So basically, I'm finding a resultant the way I would find a resultant back in chapter 2. Okay. But what's AC equal to? B squared over R. Make sure you get your parentheses in the right spots. Oh, and what are we supposed to find the frequency, actually? So remember how are frequency and period related? One over period. So that's going to be 1 over 2 pi times the square root of G over L. And we just substitute in. And it gets kind of messy. But if you had numbers, you could figure it out. Okay, we good? We got it? Right, then let's try one with a physical pendulum. And what I like about this problem is it kind of walks you through all the things that you need to think about. So it's page 438, number 41. If someone would read it for us, please. Over the clanging of the heater. Yeah, but I've dressed like it's spring. Do you know how many layers I left the house in? Because my house is like a normal temperature. And then it's like 32 outside. And I come here and it's like 78. I did that last week, but the ice storm was like, I tried and you slapped me in the face. So yeah, it's like there's limits. What? Yeah. I'm with you 100%. All right, somebody read me the problem through part A. Okay. Oh, hang on. I want it that way. Just makes more sense with my notes. Okay. So We have a rod attached to a disc, is it? Okay. Okay. And they did. They want you to practice your units. Okay, so we know that the mass of the disc is capital M. It has a radius R. We know that the mass of the rod is little m. Yes, I did. And then the length of the rod is m. And part A says find what? What are we finding in part A? We're finding the rotational inertia of the whole system. And so I really have two separate parts here, my rod and my disc. So I can say that I is I rod plus I disc. So it doesn't really matter, but we'll take the rod first. So where are you going to have to go? .2 or 9.2 or whatever it is, but I think it's 10.2. So you need your book. You need to go back to table 10.2. It's a thin rod. It has no radius. Casey, what do you see? Actually, before you see anything, tell Sari what page you're on. Thank you. Yeah, so is it rotating around? Look at the pictures. It's rotating around one end on an axis that's going through the diameter. What? Okay, so we're going to have to use the parallel axis theorem. So it's, just so that everybody remembers, it's the rotational inertia of the rod through the center of mass plus what we have from the parallel axis theorem, which is mr squared. And it might be the other m. Okay. So Casey says that I center of mass is 1/12 ml squared. And then what's h? L over 2, because what's h supposed to be, Casey? The axis of rotation and the center of mass. Okay. So you guys figure that out, and then you figure it out for the disk, okay? I'll be back in a minute.